Simulating the debris with rigid bodies looks awesome, and the collisions and behavior you get are much more natural. And Bullet is pretty good at simulating lots of pieces fast, but sometimes if you find it too heavy to add the debris with rigid bodies, you can use an instanced particle version instead. So for our pop sim, we can actually use the same exact source points that we used for the RBD version. However, we don't need that geom ID for our pop source. That's more specific to our RBD setup. So I'm just going to move that to the RBD version. And then we can use the points without the geom ID for this particle version. So we'll start by just creating a DOPNet and connecting our source points to the first input. Then you can dive inside and create a pop solver. Then connect that to the output and create a pop object. Connect that to the first input of the pop solver. And we'll need a pop source. And connect that to the third input of the pop solver. And we can add our standard gravity force. And add a ground plane collider, making sure that the order that it's connected to the merge is correct. Now for particle sims, you can emit particles from the geometry directly. That's our RBD geometry. But usually I prefer to exactly create the points and SOPs that I want to use in my particle sim. So if I want more points in my sim, I would generally increase the number of scattered points and SOPs rather than emitting from a surface and increasing it in the pop source. So on this pop source, I'll go to the emission type and set that to all points so that it exactly emits the points that it's getting from its input. And for that geometry source, I'll set it to the first context geometry. And if you go to the Attributes tab, you can see that by default it will pick up the velocity from those source emission points. And for the RBD version, we delayed our start frame to 986 because our geometry wasn't moving at 985. But just to show you an alternative, you can trim your source geometry based on its velocity. So go to the trail SOP, where we set the velocities on those inside primitives, and then we'll add in a delete after the trail. We'll set the delete operation to delete by expression. The entity will be points, and that filter expression will check the length of our velocity vector, and if that's less than 0.01, then it'll delete those points. I'll rename that to delete slow moving. So now if we display that, you can see it's deleting our geometry at 985, so we won't have any points scattered there. And as we move through the sim, you can see that it's not deleting them once they're in motion. So with that little change, we can leave our particle DOPNet set to start at frame 985. I'll rename that to particle debris and display it. I'm also going to template display the RBDs so that we can see the particles in context. And if you play through our sim now, you can see we have some bouncing particle debris. The behavior is pretty wrong. It's just sliding and bouncing far too much, but it's a decent start. So to get that behavior more under control, let's go back to our DOPNet. And on the pop object, you'll see that the physical properties have the friction defaulted to 0. So let's try setting that to 1 and turning the bounce down to maybe 0.05 as a starting point. And I have my display pinned outside of the DOPNet so that I can see everything there while I'm making changes in the DOPNet. And if we play through the sim now, you can see much more reasonable behavior. It's maybe sticking a bit too much, so you can spend some time to play around with these parameters to get it to look as natural as possible. So if I set that bounce to 0.5 and friction to 0.3, that's looking a lot better. We can also change the amount of velocity inheritance. So right now it's inheriting 100% of that velocity, and it might look a bit better if we turn that down a bit. You can see what 70% looks like. And it looks like our sim isn't reinitializing when we change some of these parameters. So when I see that happening, sometimes I will go to that DOP.NET and expand our parameter view here, and I'll pin it there, and then make that real small so it's just big enough to see that reset simulation button, so that while I'm working inside the DOP.NET here, we still have the reset sim button available right there. So now we can see what this looks like with a bit less velocity inheritance, and that's looking a bit more natural. So now we can start setting up some instances on these points, and I mentioned that we don't need the geom ID randomized on our source points for the sim, but I'm going to copy that geom ID for after the pop simulation. So if you paste that after the DOP.NET and connect that up, then this will enable us to control which instances are attached to which points after the sim. So if you cache out this DOP.NET output, it's nice to have the flexibility of changing how your instancing is set up after the simulation without needing to rerun the sim to change your geometry IDs. And because we copied that geom ID randomize from the RBD setup, it's already set up to give us valid values for the number of instances that we have. And rather than connecting this over here, I'm going to object merge it instead so that our network doesn't turn into a confusing spider web. I'll call that object merge instances and point that to ... instances. And we'll create a copy stamp. Connect the points to the second input and the instances to the first. And we'll drop in a blast. And on this copy SOP, go to the Stamp tab, turn on Stamp Inputs, and then specify the geom ID attribute to be stamped onto the copied geometry. And I'll rename that blast to isolate piece, and then we'll use our standard stamp function to just fetch one piece of our instances. So that stamp is checking this copy debris instances for that geom ID attribute with a default of 0, and we can flip that to delete non-selected. And then if you display that copy debris instances, you can see our instanced particles. And I'll drop in a null so that we can see that without that point display overlaid. I'll call that out instanced pop debris. Now if we play through our sim, you can see we have all of this detailed particle debris, but those pieces aren't rotating at all. They're just keeping their initial orientation. In addition to not rotating, I'm also seeing another problem with our instancing here. It looks like all of the points are picking up the same piece. And you can also verify that by middle mousing on our out null, and you can see there's only one unique name there. So if we double check our copy stamping, we'll see if there's an obvious problem. And sure enough, this attribute stamp has to be ID in capitals. So if you capitalize that D, then our instancing works correctly, and we're now getting different instances across all of the points. Now to add the rotation to all of our particles, we can randomize the angular velocity just by setting a random W, and we'll set the min and max to -1 and 1 for X, Y, and Z, and I'll try a global scale of 10. And we can drop that just before our DOP.NET. And if we play back this sim, it's not going to have any effect yet. Now this will be a little bit more obvious if we turn off the template display for our original RBD sim, and then if you play through these particles, you can see they're just maintaining the same orientation throughout the whole sim. They're not rotating at all, despite setting that angular velocity. Now one of the non-obvious things about setting up this angular velocity is that it'll have no effect unless we set an orient attribute on all of our pieces. So to set up that random orientation, we can use another attribute randomize, and we'll use orient for the attribute name. We'll set this to direction or orientation, and since the orient is a quaternion, that means it needs 4 values, so you can change the dimensions to 4, and then we can reset our sim. So now when you play this back, you can see all of our rotations are working correctly. However, the rotations might be working correctly, but they're never going to stop spinning. They're going to maintain that angular velocity forever. Now there are a few different ways that we can affect that spin. If you go inside the DOP.net, we can drop in various pop modifiers underneath the pop source here. And to add some drag on the rotations of these particles, you can use this pop drag spin. For this, I'd probably start with some very low values. I'll try 0.05 for just a little bit of drag on that spinning motion. And this drag spin will help a lot, but it's still possible that pieces that have completely come to a stop might still be spinning. So to ensure that stopped pieces aren't still rotating, we can use a pop wrangle, and then use this bit of vex and the wrangle to check the speed of that velocity using that length function. And if the speed is less than 0.1, we're multiplying the angular velocity times 0. So I'll call that wrangle no rotation on slow moving. And we can also use the pop speed limit to control both the velocity and the angular velocity of our particles. This is much like the bullet version, where we can turn on a maximum speed to avoid any fast moving pieces. I'll just set it to something somewhat high, like 50, just in case there are any major impulses on any of those particles. Now this pop speed limit is really just a fancy way of setting attributes on the geometry. If you check the spreadsheet and then go to that speed max attribute, you can see that's set to a value of 50, which matches that value that we set in this DOP node here. So if you want to, you could just set that in the wrangle instead. So if you go to your pop wrangle and set the speed max attribute to a value of 55, and then check the spreadsheet, you can now see that the speed max attribute matches what we've set in the wrangle. So it's really personal preference whether you use wrangles or the pop DOP nodes to set these attributes. Now I'm also going to set a spin max attribute in this wrangle based on the speed. So we first calculate that speed based on the length of the velocity vector, and then we'll use a fit function remapping that speed. So if it's a speed of 0, then we'll have a spin max of 0, and a speed of 2 or higher will give us a spin max of 10. And now that this wrangle is no longer just controlling our rotation, I'll just rename that to particle limits, and we'll see what this flipbook looks like. So now our new simulation is looking much better. We have all of our pieces rotating, with those rotations falling off over time and as the piece slows to a stop, and it looks a whole lot more realistic. Our rotations still don't look exactly like they should. This is why rigid body sims are so much better for close-up shots like this. And you could potentially make this look a bit more realistic if you had all of the rotations rolling in this direction instead of completely randomly, because that would sort of match the direction that everything is moving. But in general, for a shot this close up, I'd recommend primarily using RBD debris, except for maybe some really tiny pieces you could use particles. It's totally fine to mix and match techniques. And the smaller the debris pieces are, the less problematic it is if the rotations aren't quite right. It's also worth pointing out that in chaotic shots, like this one we're working on in the class, you probably wouldn't notice some weird rotation inaccuracies. You just have so much stuff getting destroyed and thrown around that those super accurate rotations are not nearly as important, especially when you factor in motion blur. So for your version of the shot, you can feel free to use either pop particles or RBD for your debris, or you can mix and match both and experiment with them and see which you like more. Now there's still one major thing we haven't yet added to our pop particle debris sim, and that is collisions, and we'll look at adding that in the next video.